Hi, welcome to Chapter 17, Additional Aspects of Aqueous Equilibria. Overview Part 1, where we're going to do the common ion effect and buffers. The common ion effect. Consider a solution of acetic acid. So here you have your acetic acid plus water, making your hydronium and acetate ion. What would happen to the equilibrium if I added sodium acetate? Sodium acetate is a strong electrolyte, so it will dissociate completely, and you will end up increasing the concentration of your acetate. So this is going to increase. So think about Le Chatelier's principle. When this increases, which way will my reaction go? So keep that in mind. So acetic acid is a weak acid, and we have our equilibrium reaction for it. Sodium acetate is a strong electrolyte, so it'll break up into sodium and acetate. The presence of the acetate from the sodium acetate will shift the equilibrium to the left, right? So if you're increasing this, it will end up shifting it to the left. When it shifts it to the left, it makes more acetic acid, but it reduces the amount of H+, thus lowering the concentration of H+. So that will increase your pH, making it less acidic. So what is the common ion effect? So whenever you have a weak electrolyte and a strong electrolyte containing a common ion, and they are both together in a solution, the weak electrolyte ionizes less than it would have if it were alone. Oof, that's a mouthful. What does that mean? So think about our previous example. When we added sodium acetate, our reaction moved to the left and we made more acetic acid. Acetic acid is the weak electrolyte. So if there is more acetic acid, that means less of it ionized. And we got rid of H+ ions, right? So the extent of ionization of a weak electrolyte is decreased by adding a solution of a strong electrolyte that has an ion in common. So the ionization of a weak electrolyte is decreased by adding a strong electrolyte that has an ion in common with it. This is called acid-base equilibria. This affects the acid-base equilibrium. And we'll also see later in this chapter how it affects solubility. So let's do an example here. So we have the common ion effect. Let's calculate the fluoride ion concentration and the pH of a solution that is 0.2 molar HF. And the K value for this is 6.8 times 10 to the minus 6. So here is our Ka equilibrium relationship. And we want to calculate the pH, so we need to find hydronium, right? So we're starting with 0.2 molar of HF. If we assume that it decreases by some value of X and hydronium and F- increase by X, we end up with X squared over our concentration of HF is equal to our Ka value. Then rearranging and solving, we get 0.012 molar for our hydronium. We take the negative log of that, we get a pH of 1.9. Now what if we added 0.1 molar NaF? What ion is in common here? The F. See this F and this F? So that's the common ion. So would you expect the pH to go up or down? Well, let's calculate it and see. So here we have our equilibrium reaction, and we are increasing the amount of F-. So if we are increasing the amount of F-, our reaction will proceed to the left, decreasing the amount of hydronium. So your pH should go up. So let's see what happens. So we have our initial values, 0.2 of HF, but now we have some F- in there from the salt, 0.1 of it. And then we do our normal ice table, and then we ignore these X values here, and we plug them in, set it equal to our Ka. We solve for X, which is our hydronium. We take the negative log of it and we get 2.85. So if you remember on the previous, let me just go back for a minute, the pH was 1.9. So we went from 1.9 to 2.85. So our pH increased. So adding F minus increases the pH. So if we look at our equilibrium reaction, we actually expected that. So here's another example. What is the pH of a solution made by adding 0.3 molar acetic acid and 0.3 moles, sorry, not molar, moles, of sodium acetate? So this acetate is our common ion. Here is our relationship. We are adding acetate, increasing this, which is going to make it shift to the left, decreasing our H plus value, right? So keep all that in mind. So here's what we start with. We have 0.3 molar of acetic acid, 0 of hydronium, and 0.3 moles or molar, since it's in 1 liter, molar acetate. Okay, as the reaction proceeds, we're going to change it by this X value. Assuming that the minus X's and the plus X really make no difference, plug everything in, we get that X is equal to 1.8 times 10 to the minus 5. That's our H plus concentration, so we take the negative log of that and we get 4.74. So the common ion effect applies to weak bases the same way. If a solution contains a weak base and the salt has a conjugate acid of the base won't dissolve as much as if it was alone in solution. So here is our weak base equilibrium reaction. If we dissolve a salt that has ammonium in it, it will shift the reaction to the left, lowering our OH concentration. This is section point 17.2, which is buffers. A buffer is when you have a solution of a weak conjugate acid base pair that resists drastic changes in pH. It only will change a little bit, so that's what they mean by buffer. It's kind of buffered. It can only change by a small amount. These solutions contain relatively high concentrations of both the acid and the base, and their concentrations are approximately equal. And they are particularly resistant to pH changes, even when a strong acid or base is added. So let's break this down a little bit. So consider a solution that contains equal moles of a conjugate acid and base pair, HF and F minus. So here is our equilibrium reaction. HF breaks up into H plus F minus. What would occur if we added OH to the solution? So if I add OH over here and over here, the OH is going to combine with my H plus and make water. So what is being used up? My hydronium is being used up. What is being created? Water. Okay. Now let's go back to our original reaction. What would occur if we added H plus to the original solution? Well, the H plus is going to combine with our F minus and make more of the weak acid. So what is being used up? The conjugate base. And what is being created? The weak acid. So here's an illustration to show how buffers work. So let's take this first half here. So we have our reaction down here, if you look. And we are adding OH. So when we add OH to HF, we're going to produce more F minus and water. So the notice this rectangle is now higher. They were equal to begin with. So now our F minus is higher than our H plus. And this is just showing you on the molecular level what's happening. So here we had our HF and our F. We added OH, and we're going to make more F minus. And on this side here, we had our, so here is our buffered solution where they are equal. We add H plus to it. That will react with some of the F minuses, lowering the concentration of the F minus and making more HF. And this is just a molecular drawing of that. So adding a small amount over an acid or base only slightly neutralizes one component of the buffer, so the pH doesn't change much. So let's summarize how a buffer works. First of all, a buffer is a solution that resists dramatic changes in pH. A buffer does this by being composed of certain pairs of solutes, either a weak acid plus a salt derived from that weak acid, or a weak base plus a salt derived from that weak base. So let's take one of the examples here. So based on reactions written earlier, what makes a buffer good at resisting dramatic changes in pH? So let's look at if we add a strong base. So if a strong base, which is a source of OH ions, is added to a buffer solution, the hydroxide ions will react with the acid. The OH will react with the acid, which is the H plus, in this acid-base reaction, and will produce water. So the acid, rather than changing the pH dramatically by making the solution basic, so normally when you added OH, you made the solution basic and the pH changed. But now, because that OH is kind of combining with your H pluses and making water, when you add the hydroxide ion, it reacts to make water, and the pH really doesn't change that much. It's buffered. Now let's take the opposite example. If you add a strong acid, which is a source of H pluses, it would be added to the buffer solution, and those H pluses will combine with the anion of the salt, and that would produce more of the weak acid. And when it does that, it takes some of this H plus out of the solution here, okay? So rather than changing the pH dramatically and making the solution acidic, normally all that H plus being in there would be very acidic. But because some of that H plus combines with the anion of the salt, it is not free ions that could change the pH. The added hydrogen ions react to make molecules of the weak acid. And that's unionized weak acid, right? So it's not going to really affect the pH. Why would somebody want to use a buffer? Well, in any application where the pH needs to be maintained in a certain range. And this is very critical in biological systems. An example of this is our blood. Our blood is buffered. So how do we make these buffers? One, we have to mix a weak acid with a salt of its conjugate base, or a weak base with the salt of its conjugate acid. Or the second way is you can add a strong acid and partially neutralize a weak base, or a strong base and partially neutralize a weak acid. So how do we calculate the pH of a buffer? So if you remember correctly, our equilibrium K, Ka for the acid, would be the hydronium concentration times your anion divided by your weak acid concentration. Okay, if we take the negative log of both sides and then rearrange it a little bit, we're going to get this relationship down here, which is called the Henderson-Hasselbalch Equation. And this only applies to buffers. So let's break this down a little bit further, how we got this. So here's our equilibrium reaction, and we wrote our Ka. If we kind of just rewrite the Ka a little bit in this form, it makes it easier to see. We're going to take the negative log of both sides of this equation and then rearrange it so that hydronium is by itself. So here, negative log, and we rearranged it. In rearranging it, this now becomes a positive. And this negative log is the P, right? So it's the pH is equal to the pKa plus the log of your concentration of your base, remember this is the base, over the concentration of your acid. So let's do an example here. What is the pH of a buffer that is 0.12 molar lactic acid and 0.1 molar sodium lactate? The Ka for this is 1.4 times 10 to the minus 4. So here we have our Hasselbalch equation, which is just the pH equals the pK plus the log of your, remember this is your base, and this is your acid. So we have our Ka value, so we do the negative log of that. We have the log of our concentrations divided by each other, and we get a pH of 3.77. The buffer capacity. So the amount of acid and base that a buffer can handle or neutralize before the pH starts to begin to change a noticeable amount. So a buffer solution cannot buffer unlimited amounts of acids and bases. You're going to reach a point where you've exceeded the buffering capability of it. Okay, and if you use the Henderson-Hasselbalch equation, pH will be the same for the conjugate acid base pair of 1 molar or 0.1 molar of each of the acid and base, because you're taking the ratios, right? However, the buffer that is 1 molar, it will have a larger capacity to neutralize more acid and base before the pH changes. The range at which the pH can vary in a buffer system, okay? Well, it's best to choose an acid when you're making your buffer solution with a pKa that is close to the desired pH that you want to buffer. So look up, determine what the pH range that you want to buffer is, and then look for a acid that has a Ka value kind of similar to your pH value. So the optimum is when pH equals pKa, and that means the concentration of your acid is equal to the concentration of your conjugate base. So why? Well, if they are equal to each other, when you take the ratio, you get a 1. If you plug that into this, that would give you 0, and then your pH is equal to your pKa. If this is the case, then the ratio here must change by a factor of 10 before you will actually change the pH. So you'd have to have the concentration of your acid 10 times more than your base, and vice versa. So if one concentration is more than 10 times the other, then the buffering action will be poor. So you want your concentrations of your acids and bases to kind of be very similar. If it's greater than 10 times difference, then the buffering is really not going to work too much. And that really means that the pH range for a buffer solution is normally plus or minus 1 pH unit from the pKa. So the addition of a strong acid or a strong base to a buffer. When you add the strong acid or base, it is a neutralization reaction. And you're going to calculate it like a stoichiometry problem to find your concentration of HA and your A minus when all of the added acids and bases react. And then you'll use your Henderson-Hasselbalch equation to find the pH. So if you're starting here, you have your buffered solution, which has a weak acid and a conjugate base. If you add a strong acid, it will combine with the conjugate base to make more weak acid. Then you can calculate the new concentrations of your weak acid and your conjugate bases and use that in the Henderson-Hasselbalch equation to get your pH. If you add a strong base, it will generate water and A minus, and then again, and it'll affect the concentration of this. So you have to calculate the new concentrations and then use the Henderson-Hasselbalch equation to find the pH. So what do we have to do? We have to determine how the neutralization reaction affects the amount of the weak acid and its conjugate base. Remember, the weak acid is HA, and its conjugate base is A minus. Then we use Henderson-Hasselbalch equation to determine a new pH of the solution. So let's do this example. A buffer is made by adding 0.3 moles of acetic acid and 0.3 moles of sodium acetate to enough water to make 1 liter of solution. Calculate the pH after 0.02 moles of sodium acetate is added. So here's our buffered solution up here. And then we go and we add a base to it, and we see what happens. The Ka for acetic acid is 1.8 times 10 to the minus 5. So here is our reaction. We have our acetic acid plus our OH from the sodium hydroxide, and that's going to give us acetate plus water. So we set up our ice table. We started with 0.3 of acetic acid and 0.3 of sodium acetate. Since the total volume of your buffered solution is not really changing, we could use moles here. Notice it says moles. And we are starting with 0.02 moles of sodium hydroxide, so that's how many moles of sodium hydroxide are. Looking at this balanced equation, so the hydroxide moles is going to be your limiting. That's what this LR, limiting reactant. So this is going to get all used up. So you do minus that concentration on this side of the arrow, and then plus it here. So now we have our new amounts at equilibrium, or after the reaction occurs. Now we could use the Henderson-Hasselbalch equation. We have Ka, and now we have the concentration of our conjugate base and the concentration of our weak acid. You plug them in and we get our new pH. So what is the effect of a base on a buffer versus water? So what is the pH if 5 milliliters sodium hydroxide is added to 1 liter of water? And then what if you add the same amount, 5 milliliters of 4 molar sodium hydroxide, to a buffered solution? So let's see how that affects it. So let's look at just adding it to the water. So if we're adding 5 milliliters of 4 molar sodium hydroxide, we need to get the amount of moles that we added. So we convert our volume to liters. That's what's being done here. And we multiply it, and we end up with our moles of hydroxide. We know our total volume. So we could divide the two, and that's our concentration of hydroxide. We can get our pOH, do 14 minus that, and here is our pH. And notice how much it changed, because pure water has a pH of 7. It went from 7 to 11.3 by adding just 5 milliliters of that sodium hydroxide. Now let's see how it changed our buffer solution. So we have 1 liter of a buffer solution that has 0.3 molar acetic acid and 0.3 molar acetate. The same amount of moles that were added in A will be added here to 0.3 moles of the acetic acid. When we do that, we end up with 0.298 moles of acetic acid. So think about your ice tables. So we started with 0.3 of our acetic acid and our acetate. We had what was our moles? 0, 0, 199, and 0.3. So as the reaction proceeds, we're going to use all this up. And we're going to add it over here. So when you sub all this up, you're going to end up with 0.298 over here, 0 here, and 0.302 here. So now we can use these values in the Henderson-Hasselbalch equation, and we see our pH is 4.75. If we just took the pH of our buffered solution without the sodium hydroxide added to it, it would be 4.74. So it only changed 0.01. Whereas when you added the same amount to water, it changed from 7 to 11. So you see how the buffering, it doesn't change as much.